Example 2.4. Yeah. So let's continue from last time. Yeah. Show that log of n belongs to little o of n. Yeah. This little o, by its definition, here, the definition of little o, the limit of the ratio of two functions is 0. For this case, we can only use the limit way. There is no inequality way. Well, remember last time, for some of the cases, we can use inequality way, but this little o way, only one way, limit way. Yeah. So here, we can only take the limit. Yeah. So let's work on the limit, calculate the limit. Yeah. All right. Here, when you do the limit, remember last time I mentioned the discrete variable, continuous variable. If you want to take a derivatives, you have to use continuous variables, not discrete variables. Yeah. Here we have that situation. Yeah. So when we start, let us consider a different version of the limit, and we change from discrete variable to continuous variable, x. X, continuous variable. Yeah. So, all right. Then we can apply L'Hopital's rule. Yeah. Now, it's legal. Yeah. When you take derivatives, it's legal. Okay? All right. Yeah. Here the base, that log log, so you may ask me, what is the log base, right? Yeah. So here we assume some general log base a greater than 1. Yeah. Yeah. Otherwise, people may use, one special log base. Yeah. 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 Here, let's just use the log base a. Then, first we check indeterminate form. In order to apply L'Hopital's rule, we need to check if the ratio takes one of the indeterminate forms. Yes, infinity over infinity, right? Infinity over infinity, so no problem. So we can take the derivatives, numerator, denominator. Denominator 1, derivative of x is 1. Numerator, some formula 1 over something. Yeah. So then we need to have the natural log of a times x. Yeah. After simplification, yeah, this limit, it's not an indeterminate form because numerator is 1. 1 determinate, right? Yeah. So you cannot apply L'Hopital's rule anymore. If you apply L'Hopital's rule here, you get a wrong answer. Okay? Yeah. But here you can take the limit directly, yeah, because denominator goes to infinity. Yeah. We know natural log of a is a positive number. Why positive number? Because a greater than 1. So natural log of a is a positive constant. Positive constant, you multiply x, x goes to infinity. So the denominator goes to infinity. Numerator fixed number 1, 1 over infinity, that's 0. Yeah. So this limit is 0. Yeah. But it's the continuous version. We want to go back to the discrete version. We can, remember last time the definition of limit, we can approach to infinity in arbitrary way, right? Anyway, going to infinity. We just take the discrete value way to infinity. that corresponds to this case. That corresponds to, yeah, if you like to write an intermediate step, yeah. Here we skip some intermediate step. Yeah. You can write that one more intermediate step, n over n, okay? Yeah. N over n, yeah, from our continuous version we get 0, okay? Yeah. So that tells us little o. Log of n belongs to little o of n. Okay? Yeah. So this is after our proof here, you can use it as the result. That means when you answer some of our homework questions, you just use this result directly. Okay? Yeah. You can use it. Yeah. Just like a theorem, use this result directly. Okay? Yeah. You do not need to explain anything to me. Okay? Yeah. Natural log of n, any log, okay? Any log. Yeah. Log of base 2, log of base 10, natural log, any log, okay? Yeah. But base must be greater than 1. Yeah. If less than 1, it's negative. It's a negative. So because our growth function cannot be negative, right? That's the reason we do not allow log of base less than 1. Yeah. Negative. We don't have the negative case. Yeah. Yeah. All right. Yeah. So here, the result is simple here, but you will see in some of our homework questions, yeah, based on my experience before, many students, they didn't realize they can use the result here. Okay? Yeah. Yeah. They're not aware of it. Yeah. Under situation with log comparing with other functions, they are not aware of this result. Okay? Yeah. Yeah. All right. Yeah. Let's look at some more results. Yeah. Similar to this one, we need a few more results. Okay? Yeah. So later you will see, yeah. The results are so simple, so you feel so natural. You feel natural. Here, it's natural, right? Yeah. But when you work on some, related questions, yeah, not that straightforward. Okay? Not that straightforward. Yeah. Because usually you answer those questions by your intuition. By your intuition. But your intuition could be wrong. Think about that. Your intuition, many times it could be wrong. Yeah. You will see that. Okay? Yeah. Yeah. I tried to give you your first homework assignment this weekend. Okay? Yeah. You will see. Yeah. Several such questions. Yeah. Your intuition could be wrong. Okay? Yeah. All right. Let me jump to last part of this module, part D. Yeah. Part D, I start with a few more examples. All right. D.1, examples of asymptotic notations, part 2. A few more examples. Okay. Yeah. 2.5, yeah. Let's look at this one. Yeah. It's a simple example, yeah, but later you will see, your intuition could be wrong. Okay? Yeah. Here we have several results. Yeah. I give all these results to you, okay? Several, 3 or 4 or 5, yeah, yeah, those, yeah. try to identify all these results in the homework questions. Yeah. All right. Show that power function n to the d. This d, you may ask, what's the d number? It's positive number. Okay? It's a positive number. Yeah. Second, here, when I prove it, I use d, a positive integer here. Actually, this result is true for non-integer number, also true. Non-integer number, yeah, I will show you. Oh, yeah, because here the assumption, we only require d greater than 0. That's it, not necessary integer, okay? Any number greater than 0, we have this result. N to the d power belongs to little o of a exponential function a to the n. A must be greater than 1. Yeah. That's the condition. All right. How to show it? Yeah, let me show it. Yeah. Yeah. So here condition. Yeah. Yeah. So here, although I say greater than, yeah, but less than 1. That's so simple, right? Yeah. Less than 1, simpler. Yeah. Yeah. All right. Yeah. All right. Yeah. So here. Yeah. Yeah. So when we start, we assume it is integer. If it's not integer, we work on it later. Our first time, we want our situation simpler. At the beginning, you don't want to work on a, relatively hard case, right? You want to work on a simpler case. Integer case is simpler. So we work on integer case first. Yeah. Why integer case so convenient? Yeah, you will see. Because our technique, we need an integer. Technique, L'Hopital's rule, we need an integer. Okay? Yeah. All right. Let's apply L'Hopital's rule here. Yeah. All right. Work on continuous variable, right? Yeah. The same way. Yeah. X, yeah, this time, x to the d, positive integer, is it indeterminate form? Infinity over infinity indeterminate, no problem. Yeah. So we are safe to apply L'Hopital's rule. Then, when you take derivative, numerator, we apply power rule, right? Power rule. So d times x to the d minus 1, that power. Okay? Denominator, derivative of exponential function, natural log of a, because a greater than 1, so this is a positive constant. So natural log of a is a positive constant. Then times the same exponential function a to the x. All right. But after we apply L'Hopital's rule the first time, still, if d is a relatively large integer, still indeterminate form. That means we can apply L'Hopital's rule another time. How about we apply second time? Okay? Yeah. If it keeps that indeterminate form, we apply all the way down. Okay? All the way. All right? So the second time, we get this form. Okay? Yeah. But sooner or later, we reach the end, right? Yeah. Yeah. Sooner or later, we get someplace, yeah, the last step, x d minus d. We apply d times. How about that? D times. So d factorial times x to the d minus d 0, x to the 0, that's 1. Then it won't be indeterminate. Yeah. It is determined, right? Yeah. But after this step, we cannot apply L'Hopital's rule another time. Yeah. Here, let's do simplification. The simplification, numerator d factorial is a constant. Because after d is given, d factorial, it is a constant. Okay? Yeah. Denominator, parenthesis, natural log of a raised to dth power, another constant. Okay. Constant, because they are fixed. These two constants, whatever the number it is, they are fixed. They cannot change. Then, exponential function at the denominator, a to the d, where x goes to infinity, this function value goes to infinity. Okay? So the denominator goes to infinity, numerator fixed the number, so the whole fraction limit is 0. Limit is 0. Okay? Then we go back to the original limit. Yeah. Okay? And we can change to the, discrete variable version, right? Yeah. If you like, yeah, so here, if you like, you'll write one more times n to the d, a to the n, the limit is 0. Okay? You write one more time, the limit is 0. Okay? Yeah. Then, by the little o definition, you get this little o result. Okay? Yeah. So we prove it. Yeah. But we prove it for d positive integer. The next question, if d is not integer, how do you prove it? When d is not a positive integer, because when you apply L'Hopital's rule, not very convenient, right? Yeah. It's hard to stop. Okay? Yeah. Although you can, you can argue, right? Yeah. You can find some argument. You can argue. Yeah. But it looks like the proof is not very smooth, right? At least not quite smooth. Yeah. Here, let me use another way. Try to show you in a smooth way. In a smooth way. Okay? All right. Yeah. All right. Now, let's assume d is not an integer. Can we find two integers, one smaller than d, one larger than d, two adjacent integers? Yeah, just cover that d. Okay? Yeah. So now we want to, can we find a d0 less than d and a d0 plus 1 greater than d if d is not an integer? Yes, we can always, right? Yeah? Okay. Yeah, we can always. Okay. All right. Now, let's just use that d0 plus 1. Okay? Yeah. All right. Now, because here when we take limit n to the d over a to the n, can we write limit n goes to infinity n to the d over n to the d0 plus 1 times n to the d0 plus 1 over a to the n. Can we write it this way? Two fractions multiplied together. Okay? The first fraction, n to the d over n to the d0 plus 1. It's less than 1, right? Yeah. The second one, n to d0 plus 1, it's an integer, right? And the second one, we already proved the first time, integer, right? Can you see this equals 0? Because each limit of each fraction is 0, right? The limit of the first fraction is 0, right? Yeah, because you can cancel out, okay? the numerator number, exponent number is smaller than the denominator number, right? The numerator d is less than denominator d0 plus 1, okay? So the denominator increases faster than the numerator, right? Yeah. So the limit of the first fraction goes to 0. The limit of the second fraction, we prove it the first time, okay? Yeah. So the whole thing is 0. 0 times 0. The whole thing is 0. Okay? Yeah. So even d is not integer, we can prove. We can use this, we can use the integer, closely related integer as the bridge. To, fill the gap. There is a gap, but we have some bridge to bridge the gap. So we get it in this way. Yeah. So this is, some common problem-solving strategy. Common problem-solving strategy. When we need to solve a targeting problem, sometimes if we solve it directly, it's hard. How do we do it? We solve an approximate problem. Not exact problem. Exact problem relatively hard. Okay? Now we solve a problem slightly different. Here, integer version slightly different from the targeting version. Okay? Yeah. But that one, there is a small gap between two versions, right? Yeah. After we solve that, simplified version, later we try to find a way to bridge that gap. That's a commonly used problem-solving strategy. So you can see how effective here. Okay, yeah. All right, after this one, then you can apply this result. But the issue is, sometimes this result tells you one thing, but your intuition tells you a different way. Your intuition, you have your intuition, right? Your intuition may tell you a different way. They are fighting. Two different ways, they are fighting. And many times, your intuition will win at the end. Here, let me give you an example. So your intuition and this here you believe this result is correct, right? Yeah. Before we try to fight your intuition, do you believe this result is correct? We rigorously prove it, right? By L'Hopital's rule. Every step is rigorous. So it is correct, right? All right. Now, I try to, challenge your intuition here. Okay? All right. D could be any positive number, right? Here, I take a very large D. How about that? Okay? I want to compare D as 1 million, how about that? Is it large? Is this function large? N raised to 1 millionth power. When n goes to infinity, do you think is a huge number? Yeah, okay? All right, so first one, we use this one, compare with second exponential function, okay? All right. Second exponential function, the only requirement is a greater than 1. That's the only thing we need. Strictly greater than 1. Cannot be 1. Yeah. Here, how about we choose a slightly larger than 1? Okay. Slightly larger than 1. How large? 1.0000001. This small. Very close to 1, right? Only tiny bit larger than 1, and we raise to nth power. Now I ask you, which function eventually grows faster? Which function eventually grows faster? Yeah. Your intuition tells you a different story, right? Yeah. Because the first one's so large, the second one is so close to 1. Although you raise to nth power, but how can that number be a large number? Think about that, all right? Right? How can that number be a large number? Okay? Yeah. Think about that, because this is one of our homework questions. Okay? One of our homework questions. Yeah. Okay? Yeah. Yeah. So think about it. Okay? Yeah. All right. Yeah. So that's why many times, because your intuitions are so strong, it's hard to change it. Okay? Hard to change it. All right. 2.6. Log base 2 of n belongs to little of root of n. Little o of root of n. Now, this one, remember our previous log n, but similar to that. Similar to that, to that example. Yeah. But here, root of n, if we convert it to a power function, power 1/2, 0.5, not an integer. Yeah. So here, let's consider the ratio of these two functions with continuous variable, so we can take L'Hopital's rule. It's infinity over infinity, indeterminate form, so we can apply L'Hopital's rule, taking derivatives. Yeah. All right. Yeah. Before we take derivative, here we just write denominator as this power function, x to the 1/2, that power. Okay? So we can apply power rule. Yeah. All right. Derivative, yeah, we apply the formulas. So this is the derivative on numerator, denominator. Okay? Then we do simplification. After simplification, we have, some constant, 2 over natural log of 2. Yeah. Yeah. Constant part, never change. But denominator x to the 1/2, that's the variable part. Yeah. When x goes to infinity, the denominator also goes to infinity. Yeah. And its limit equals 0. Yeah. Then we go back to the discrete variable version, so we get the log base 2 of n belongs to little o of root of n. No problem, right? Yeah. Yeah. So another rigorous proof. Yeah. So you can use this result after the proof directly. Okay, all right. Yeah. Then, next one, this time it's a similar one. Yeah. Similar version. Here you can see the natural log. This is the third example we work on log function. Yeah. The third one. Yeah. So this is the last one. Last one, log function. After this example, so we complete this topic. Okay? Yeah. Last one, we only need little d is a positive number, that's enough. We don't need more. Okay? Little d, we only needed any positive number. It's enough. And then this result tells us natural log of n, not necessarily natural log, you can use other log function, also okay. Here, I just, for convenience, I take natural log as a representative of general log. If you use general log, still correct. The answer is still correct. All right. So the natural log belongs to little of n to the dth power. Let's prove it. L'Hopital's rule again. Discrete version. Infinity over infinity, indeterminate form. So we can apply L'Hopital's rule legally here. Derivative numerator 1 over x. Derivative of denominator power rule d times x to the d minus 1. D positive number. Any positive number. Okay. Then we do simplification. Cancel out, x. Simplification, we get this expression. Limit of x goes to infinity, 1 over d constant times x to the d. Constant part, fixed. Denominator x to the d, remember, d is positive. D is positive. So x power function to some positive exponent must go to infinity, right? When x goes to infinity. So denominator always goes to infinity. So the final fraction number goes to 0 when x goes to infinity. 0, limit is 0. Then we go back to the discrete version. We have the little o, right? The discrete version, Continuous version, we can, use the discrete special case for the limit result. So we get this little o result. This little o result. Okay? All right. Now, after our proof, you can use this result from now on. But try to, when you apply this result, sometimes you may need to fight against your intuition. Another time. Another time. All right? All right. Here, I'd like to show you. So here, there's already one example. Okay? You think about it. Here, let me give you another example. Okay? All right. Compare these two functions. One is natural log of n. Okay? When n goes to infinity, this function goes to infinity. The other one, now, that's n to the d. Okay? N to some d. D only needs to be a positive number. Here, can I give you a very small positive number? 0.0000001. How about that? The exponent is so small, close to 0, but not 0. Okay? Very close to 0, but not 0. Your intuition tells you this function could be very small, right? Yeah? Exponent is so small. So your intuition tells you this function could be very, very small. Yeah. All right? But when we do comparison between these two functions, which one eventually wins the race, growing race? Yeah. Think about these two examples, one here, one here. Okay? Yeah. Two examples. All right? Yeah? Yeah. All right? Yeah. So we finish this topic. Yeah. 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 This topic, these two results, basic results, important. Yeah. Yeah. One here, one is this one, another is this one. These two basic results, very important. Okay? Yeah. All right. Then next topic. Deep on 2, introduction to brute force method. We applied brute force method a few times. Yeah. Yeah. But here, so let's look at it another time. So then we will complete discussion of this simple method. Yeah. All right. First, description of brute force method. Yeah. Properties of brute force method. Some simple properties. Yeah. It's a straightforward approach. Yeah. Probably you can say simplest method when we solve any computing problem. We treat brute force the simplest. Okay? Yeah. And you can always apply it to a problem. When you do not have any idea, when people do not have any idea to solve one particular problem, one thing they can do, the brute force method. Okay? At least you can start doing something to get some experience. Brute force. Yeah. In general, it is not the best algorithm. Yeah. In general, you cannot expect good performance from the brute force method in general. Okay? Yeah. Yeah. It is usually used as the starting point for more advanced algorithms. Yeah. Because you need to understand the problem. You need to build up some experience. So then, some people, so they use the brute force method to get started on one particular computing problem. Yeah. All right. The efficiency difference between the brute force method and the more advanced algorithm could be huge. Yeah. You have seen it. Yeah. In our module 1, when we evaluate polynomial, you have seen it. Yeah. Horner's rule versus the brute force method. The difference is huge. Yeah, we can say it's huge. Okay? Yeah. Yeah. So we compared. Yeah. All right. Yeah. All right. Example, the polynomial evaluation problem. Yeah. All right. That means in order to get a good one, like the Horner's rule, you need to make a lot of effort to get a good result. Yeah. All right. Then, now we want to apply, so here, although, close to the brute force may not be, because sometimes it's hard to describe exactly what is the brute force, right? Yeah. Yeah, some algorithms, you need to do some work, do some simple work. Yeah, yeah. to get some algorithm, yeah, but you can treat as very close to the brute force. Yeah. Yeah, you did some, little processing work. Yeah. All right. So now, let's work on our problem number 4. Another time, revisit. The first time, selection sort. Now we want to sort it using a different way. Yeah. Second time. Yeah. Yeah. So we call it revisit this problem. Yeah. Another time. All right. Given an array, how to sort it in ascending order. Yeah. You may ask me why we need to do it another time. Okay? Yeah. One of the reasons people may explain in this way, because you want to improve. Yeah. The first time, the result, we are not quite satisfied. We want to improve our efficiency. Yeah. So that's one of the typical arguments. Another one here, I want to use another perspective to view this question. Yeah. Yeah. So sometimes we solve one particular computing problem using different solutions. You can view in this way. You can view in this way. From the problem-solving view. Problem-solving view. Yeah, here. Yeah. Because we know for this class, we want to develop our problem-solving skills. Yeah. That's important. We want to prepare ourselves in the future. We want to be strong problem solvers, okay? Solving real-world computing problems, we want to be strong problem solvers. Yeah. From that particular aspect, yeah, we view like this. Yeah. All right. Why we need to solve it another time, our view, we treat a problem as a carrier of a set of thinking methods that result in different solutions. So that's the view. Yeah. This problem here, we use sorting problem. This is a computing problem, right? Sorting given array, computing problem. This problem, it has several solutions. Yeah. Each solution has different idea, okay? Different thinking, problem-solving thinking method. Yeah. All right. So then, this problem we can treat as a placeholder or, carrier. It carries several different solutions. Each solution has some special thinking way. Thinking that way, okay? Yeah. Yeah. For this class, our sorting problem, we may need to use 6 or 7 solutions. Yeah. 6 or 7 solutions. Then, this problem carries 6 or 7 different problem-solving thinking ways. And those thinking ways could be valuable for your future other problem solving. Okay? Yeah. So that's another view, another understanding. Yeah. The value. So why we use so many different ways to solve one same problem. Yeah. Because we value those problem-solving thinking ways. They are valuable. Problem-solving thinking methods, they are valuable, right? Yeah. Because they could be used to solve other, various other computing problems. Yeah. Yeah. But how do we carry those thinking methods, right? Yeah. How do you store? Yeah. How to carry, right? Yeah. Here, this problem can carry those solutions, thinking ways. Okay, yeah. Another way of understanding. Yeah. All right. The thinking methods are important to help us solve other computing problems. Yeah. That's what we want to have. Okay? Yeah. So we don't want to throw away all these valuable thinking methods. Okay? Yeah. So we want to keep them, yeah, as our problem-solving tools in our toolbox. Okay? Yeah. Toolbox. So we can use this toolbox to solve many other new computing problems. That's our understanding. Okay? All right. A view based on special property. Now, we need to develop some new solution. But how do you get a new solution? If you use your old view, yeah. Remember, when we apply the selection sort, we took one specific view of the problem, right? Yeah. Finding the minimum, that's our view. Okay? Here, we want to change our view. If you still take that same view, you won't get a new solution. You have to look at the same problem in different view. Yeah. Here, we need to change our view. How do you change your view? We need to discover a different special property. If you find a different property, based on that property, your view would be different. So we can develop a new solution. Yeah. So let's work on this line. Yeah. Observation. Let's view our current sorting problem another time, but you need to observe, make observation on this problem closely, try to find something new, useful, new property that is useful. Yeah. So let's view it. What is that property? Interesting property. Okay? Yeah. 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 All right. Yeah. It's not easy. Yeah. Discover some new property, that's not easy. Yeah. Yeah. If you can find one, then it's halfway. Yeah. Yeah. Because if you find some good property, that's halfway to the solution. Okay? All right. So now, let's draw this diagram. Try to discover that new property. Yeah. So this is a typical array. Typical array. Okay? Yeah. So the elements in the array, arbitrary order. Yeah. Now, we want to do the comparison, right? Yeah. When we do sorting, basically we need to do comparisons. Yeah. All right. Now, let's compare two elements in the array and see what property we can observe, we can discover. What property? When we look at any two elements in the array, yeah, what is the basic property you can observe between these two elements? Let's look at that. Okay? Yeah. All right. out of order probably, yeah, because sometimes they are in ascending order. If when we select two elements from the given array, if these two elements in ascending order, that means the second one is greater than the first one, then that property matches our goal, right? Our goal is we want to make the whole array in ascending order. Here, when we only look at these two elements, they are already in ascending order, then we feel happy, right? Yeah, yeah. Nothing wrong because they are already in ascending order. Yeah. But there is something wrong if they are out of order. That's against our goal, right? Yeah. Yeah. Because that's opposite to our goal. Our goal, we want to make ascending order, but we find two elements that are in descending order, okay? Descending order. So that's opposite to our goal, against our goal. That means in order to make it closer to our goal, do we want to swap these two elements to make it ascending order again, right? We want to fix the problem, okay? Yeah. This is our observation, okay? This small analysis process, that's our observation, okay? All right. So here we want to focus our attention on this out of order phenomenon, okay? Out of order, that's a special phenomenon, right? Yeah. Now we want to focus on those elements or those pair of elements that are out of order. We want to focus on that part. Okay? Yeah. All right. How do we focus on that? Yeah. All right. Yeah. So here we want to look at our critical property. Yeah. We find something, yeah. That property, that phenomenon looks useful. Yeah. So we want to study it. Okay? All right. If the array is not sorted, what property would you have? If array is not sorted, what property would you have? Okay? Yeah. All right. There must be two adjacent elements that are out of order. Is it true? If an array is not sorted, then we say there must be two adjacent elements that are out of order. Can you see that? Two adjacent. Yeah. You may hard to see why two adjacent, right? Yeah. Now, let me remove adjacent. Do you feel better? If the array is not sorted, yeah, let's temporarily remove adjacent, that word. Okay. Can we say there must be two elements that are out of order? Two elements in the array. Okay? Yeah. The later one is smaller than the earlier one. Okay? Yeah. Yeah. The later one smaller than the earlier. Or the one with larger index is smaller than the one with smaller index. That's what we mean out of order, okay? Descending order. Yeah. If an array is sorted, can you always find those two elements? You can use contrapositive method. If you cannot find any two elements, the later one always greater than the earlier one, then you get the whole array already sorted, right? Yeah. So that's the contrapositive thinking. Yeah. So you can find one pair, yeah. Yeah. Not necessarily adjacent, yeah. But here, after we add this adjacent, it makes a little harder to see a little harder to, but you can still get it, right? Adjacent. Yeah. Because if every two adjacent elements are in order, ascending order, you will get all elements are in ascending order, right? Yeah? Because you just look at it. You start from the first adjacent pair, if it's ascending order, second ascending pair, also ascending order, and so on, all the way through the last ascending pair, also ascend, then the whole array ascending order. Right? Yeah. So if it's not the whole array is not sorted, this chain must break somewhere, right? You have a chain, right? From beginning to end. There is a chain, ascending order. But if we know at the beginning our condition is the whole array is not sorted, then that ascending chain would break somewhere, right? When it breaks somewhere, that pair is not in ascending order. That pair is out of order. Can you see that? Yeah. If you can see that, you'll find some new property. That's the new property you discovered that could be useful to give us a new solution. Okay? Yeah. All right. Yeah, so here I give you the reference in the textbook, section 4.1. Yeah. All right. Now, in order to discuss that out of order, in order, that phenomenon, that property, we introduce a new concept called inversion concept. What's that inversion? Yeah, definition. A pair of elements A sub I and A sub j, these two elements, AI, AJ, is called an inversion, then they should satisfy this condition. The index I less than j, but the values, AI value is greater than AJ value. That means there are these two elements. If we look at these two elements, they are in descending order, not ascending. Okay? Opposite. Yeah. Descending. Opposite of the ascending order. Okay? Yeah. Descending. Yeah. So that we call inversion. These two elements form an inversion. Inversion concept. Okay? Yeah. After we define this concept, then we can use the number of inversions to tell us if an array is sorted or not. Yeah. In our discussion, we will use the number of inversions to tell us how far away a given array is from the sorting state. Yeah. The sorting state. How far away? Is it very far or very close? We just look at the number of inversions. If the number inversion number is big, yeah, we may feel it's far away. Okay? If the number of inversion is a very small number, then this array is very close to the state of being sorted. Right? Yeah. So that's our new understanding. Okay? Yeah. All right, so now, let's continue. If the array is not sorted, what would we have? Not a sort. Yeah. So here you can see we repeat above property, but this time there must be an inversion. We use inversion to restate the above statement. Yeah. The first version we didn't say adjacent pairs, yeah, there must be an inversion. The pair for this inversion may not be an adjacent pair. Okay, may not be an adjacent pair. Yeah. So we can see that's one of the two versions. There must be at least one inversion. Yeah. Otherwise, if there is no inversion, you can see the array is already sorted. Okay, all right. Then another version, if the array is not sorted, then there must be an adjacent inversion. This time we add the word adjacent inversion. Okay, yeah. The same meaning we already discussed, right? Yeah. So we only, here, this version, we only take this inversion concept. We change the wording using this inversion name here. Yeah. Yeah. All right. This property, this is the critical property we discovered for our new solution. All right. Next, with this new critical property, how do we develop our new solution? Think about how, yeah, so here, because after we discover this critical property, we're halfway for the final solution. Halfway there for the final solution. Okay? Yeah. But how to complete the remaining half? Remaining half. Yeah. How to apply this property to make the whole array sorted? Yeah, so let's do it. Yeah. All right. Yeah. Here you can see the change, first version to second version. The first version, we take the global view, yeah, because the first type of inversion, we didn't say an adjacent inversion. That means it's a global inversion. How about that? The two elements that form inversion could be anywhere in the array. Anywhere, so that's a global description, right? Yeah. But the second way, we narrow. Yeah. We narrow down. So we do not need to look at the inversions globally. We only look at the adjacent pair for the inversion. So that one we call the local view of inversion. Local inversion, global inversion, and a local inversion. Okay? Yeah. These two versions equivalent. Yeah. But the local view is more friendly, right, for us to get a solution. Global way, not that friendly, right? Global view. Global inversion, not that friendly. Local inversion, more friendly. Because local inversion, it's easier to fix. It's easier to fix, right? Local inversion. You know, you swap to an adjacent. Easier. Global, you can do swap, but, you know, it's hard to identify the global inversion, right? It's easier to identify local inversion, right? Yeah. Global, in order to discover global, you need to do a lot of work. Okay? Yeah. Yeah. So here we like to take the local view for the inversions in a given array. Yeah. All right? So that's our solution. Yeah. Now we are ready to finalize our solution. Yeah. How to fix it? Yeah. All right. Swap. Every time we swap two elements in an inversion, we fix. We kill that inversion, right? We eliminate that inversion. we remove that inversion. Okay? All right. Now, implementation idea. All right. Remove all the local inversions by local swaps. How about that? Yeah. Our goal, we want to remove all local inversions. If all local inversions are gone, then the whole array is sorted. Yeah. Whole array is sorted. Yeah. All local inversions disappear. Okay? Yeah. That means no inversion. Yeah. Because if you have global inversion, then you must have a local inversion. You must have an adjacent inversion. Yeah. Otherwise, if there is no other adjacent local inversion, then whole array is sorted. Okay? Yeah. All right. So now let's work this first sentence. This is the general idea. Yeah. But we need to fix the details. We need to complete the details. Yeah. All right. Step 1, start from first element for each scan. Every time you scan the whole array, yeah, from the first element. Okay? Yeah. All right. Do swaps one by one from left to right. Yeah. If you discover some inversion, then you just do swap. Okay? Yeah. If no inversion, then you move to the next adjacent pair. Yeah. And so on. Okay? All right. Yeah. Yeah. All right. Yeah. 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 All right. Yeah, for the swap, if necessary, because sometimes you do not need to swap. Okay? If there is no inversion, you do not need to do swap. Yeah. All right. Stop at the first in-place element. Here we use this in-place concept. Yeah. 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 I remember I mentioned that, right? Remember when we work on the selection sort, one element we put in place. Yeah. The minimum, we find that minimum, so that minimum is at its right place when the whole array is sorted, so we call it in place. Yeah. We use that terminology. Yeah. Here, the same concept, same thing, in place element. Yeah. Because when you do that swap, round by round, each round, think about, you move one of the elements in place. Because when you do that swap, local swap, yeah, the largest element is always swapped to the end of the element, to the end, the largest. Because the largest one keeps moving, okay, keeps moving toward the end. Okay? Yeah. When the largest one reaches the end, it is in place, right? It reaches the end, it's in place. Okay? If it is in place, the next round, we do not need to look at it because it's already in place. We can eliminate that element already in place. So we do another round, local swapping, and our second round, we put the second largest element in place, right? And so on. Okay? Yeah. All right. Now, yeah, so we, our observation. There is one element in place for every scan. Every scan. So when we do that, local checking first. Yeah? Checking for inversion, okay? If there is inversion, then we swap them, okay? Yeah, yeah. So there is one element in place for every scan. The last one is guaranteed to be in place, okay? All right. The in-place element of each scan appears at the end of the current array. Yeah. Because after we eliminate those elements in place, then we have a current shorter array. Current shorter. Okay? Yeah. So when we do that, we find another element in the current array that is in place at the end of this current array in place. All right. And the current array is a subarray that excludes all the in-place elements. Because the trailing, the tailing, end part, the end part, those elements are in place. All right. And then finally, all the elements are in place. All right. And this is a new sorting algorithm. And this one, actually, you learned this algorithm before. After my description, some of you realize you learned this before, right? Yeah. That's the bubble sort. That's the bubble sort, because it looks like a bubble, okay? When you do local swap, moving from left to right, just like a bubble moving from left to right, right? Yeah. So, that's the, you're familiar with this name, bubble sort name. So the idea, but when you learned the first time, you didn't use inversion concept, right? You just do it, okay? You just, for loop, two nested for loop. You just work on it, okay? That's it. But here, we discuss the properties, ideas, concepts, all those problem solving, thinking. All right, and we get the solution. Efficiency analysis, we need to count the number of comparisons. Efficiency analysis similar to that of the selection sort. Selection sort, because we know every time we do one scan, we need a certain number of comparisons. That number the same as the selection sort. All right. And here, before we finish this slide today, let me ask you this question. What is the basic operation? When I ask you this basic operation, because when we have two operations, one comparison, another swap operation, right? When we find inversion, we swap them, two elements. So here I want to ask you, is the comparison should be the basic operation, or the swap operation should be the basic operation? Here. Basic operation, that means the one that contributes the most to the response time, okay? So you spend a lot, response time. Which operation contributes the most to the overall total response time? Swap or comparison? Can you see that? Which one contributes more? Swap or? Swap, basically, a few assignments, right? So, do assignment here, there, 3 assignments. That's one swap operation. Here the answer, because we do not have much time. I need to finish it quickly. We do not have much time. The answer is comparison is the basic operation. Swap is not. Why? You can see it easily in this way. When you have an array already in ascending order, you still need to do comparison, right? But you never need to do swap because there is no inversion, no swap. But you need to do comparison all the way from beginning to end. You cannot save any comparison. The number of comparison you need, the same as the number of comparison you need in selection sort. You cannot save any. But swap, no. You do not need to do any swap. Okay? Yeah. Swap, that's why swap does not contribute as much as the comparison operation. Okay? All right. That's it. Yeah. Next time we finish last topic. Okay? String matching problem. Yeah. Then we finish the whole module.